Hello there, geometry students. Today we're going to be taking a look at a postulate that we can use to prove that two triangles are similar. It's going to be called the AA Similarity Postulate, which stands for angle-angle similarity. Just as a real quick review, let's remind ourselves what it means if two polygons like triangles are similar, right? So I'm going to use this space up here. I'm going to say that similar polygons have two things true about them. First of all corresponding angles will be congruent. Um, Sometimes we talk about how that means that the two polygons have the same shape. The corresponding angles are congruent. And the other thing that will be true about two similar polygons, triangles or otherwise, is that the corresponding sides will be proportional. And of course, we've talked about how what that means is if I set up a ratio of one pair of corresponding sides, that ratio would be equal to any other pair of corresponding sides set into a ratio. So that's the definition of similar polygons. All the corresponding angles are congruent and all the corresponding sides will be proportional. But sort of like what we learned about with congruence, we don't actually have to do all of this work. We don't have to show that all of this is true in order to say that two triangles are similar. We can take a few shortcuts to prove that two triangles are similar. And so in this section as well as the next section, we're going to be looking at three of those shortcuts that we can use to prove that two triangles are similar. And so the first one is called AA, or angle-angle similarity. And so if you need to make yourself a note, AA stands for angle-angle similarity. And so what the angle-angle similarity postulate states is that if two angles of one triangle are congruent to two angles of another triangle, then the triangles will be similar. And so what this shows us is, even though this is our definition of similar, corresponding angles are congruent, all of them, and corresponding sides will be proportional, we actually don't need to know anything about the sides if we have two of the angles that are congruent. And of course, we can remember that since we're talking about triangles, we actually know if two of the angles are congruent between two triangles, because they have to add up to 180, we actually know that all three angles are congruent, but we can shorten that down to just saying that if two angles are congruent, then the two triangles will be similar. And so let's take a look at how this might be used in a proof to start with. So I'm going to scroll up here a little bit. I'll keep that AA similarity postulate on the screen so we can refer to it if we need to. But we're going to do this proof right here. And so we have this diagram with a couple segments kind of crossing and then a set of parallel segments on the sides. And so we got segment AC parallel to segment BD. And we have to prove that these two triangles must be similar. And since obviously we just learned about angle-angle similarity, that's probably the direction we're going to try and go. So we're going to try and find a pair of angles between these two triangles that would be similar. And we keep in mind that the given information is usually something that we're going to want to use. So our mind should be going, well, if I have a set of parallel lines, how does that potentially lead to congruent angles? And since I have a couple transversals here that are connecting those parallel lines, or they're intersecting both the parallel segments, then you should start thinking about some of those special pairs of angles that will be formed when you have parallel lines cut by a transversal. Now we also notice that we have a couple segments crossing here in the middle, and so what that's going to create is a pair of angles here and here that would be congruent because they're vertical angles. That, combined with the fact that angle A right here would be congruent to angle B down here because they're alternate interior angles, that would give us our two pairs of angles that are congruent. If we wanted to, we could also say that angle C right here would be congruent to angle D over here, because they're also alternate interior angles. But we don't have to go that far. We just need two pairs. So we got a pair of vertical angles that are congruent, and then we got a pair here along with this over here. These are our alternate interior angles that are congruent. That would be our two pairs, and then that would allow us to state that these triangles are similar. So how is that going to look in a proof? We'll put our statements right here. That wasn't a very good S. Our statements right there, and our reasons over here. And our first statement, like it usually is, will probably be our given information. That segment AC is parallel to segment BD, and that is given. From that, we were able to conclude that we had a pair of alternate interior angles that are congruent. So let's go ahead and state those. We had angle A, which was congruent to angle B. And those are congruent because alternate interior angles are congruent. And it's a longer statement technically. It's alternate interior angles are congruent when two parallel lines are cut by a transversal. But we could probably shorten that down to just saying alternate interior angles are congruent. So that's one pair of angles. So if you wanted to put yourself a little note there that that's a pair of angles, we would need another pair. And we said that what could be that those vertical angles right there are congruent. So we can say this is right here, this is angle AOC. That will be congruent to this angle right here, which is angle BOD. And those are congruent because they are vertical angles. So we say vertical angles are congruent. And that's our second pair of angles. And so what that leads us to be able to say is, since we have two pairs of congruent angles between our two triangles, we can say the triangle AOC is similar to triangle BOD. And our reason will be angle similarity. And so we just use the angle similarity postulate to prove that these two triangles here and here are similar. They're not congruent. We didn't prove that they're congruent. We proved that they are similar because they have two pairs of angles that are congruent between them. Let's take a look at another proof. If you wanted right now, you could pause this video and you could try the second proof on your own and then come back and see if you did it the same way I'm about to do it. Or you can just let this play and we'll take a look at how this one might work out. So we have this diagram here, and the given information tells us that we have a couple sets of perpendicular segments. So RH perpendicular to AF, and this says AF perpendicular. That's not right. That's supposed to be AB. A little typo there on my notes. AB is perpendicular to BF. We also know that angle 1 is congruent to angle 2. Now, of course, we're probably going to be using the angle similarity postulate here, so we need to start thinking about what pairs of angles might be similar between these two. Even though our proof statement isn't ultimately that we want to prove these triangles similar, our proof statement is that if I multiply HR times BF, it would equal BA multiplied by HA. Okay, so let's just see where this takes us. Let's see if we can use what we know and start a proof that eventually might take us to a place where we can end with this statement. Sometimes that's a good strategy on proofs, is just to start with what you know and see where it takes you. If it takes you to the right place, good. If not, well, you just start over and you see if you can do something different. So what we know is we know that angle 1 is congruent to angle 2, and that's a good start because that's one of our pairs of angles that would be congruent. And since I have these two sets of perpendicular segments, we know that that's going to form these two right angles. And since right angles have measures of 90 degrees, they're going to be congruent to each other. And so that would allow us to state that these two triangles are similar. And let's start there and let's see where else we can go with that. So let's start our proof over here with our statements and our reasons. And we'll start off, I'm actually going to start off by saying angle 1 is congruent to angle 2 with the given information. I know it's listed third over here, but that doesn't mean we can't start with it first in our proof. So that's a pair of angles that are congruent. Now I'll go to my other piece of given information, which is segment AB perpendicular to segment BF, and segment RH perpendicular to segment AF. I'll put those both in the same statement since they are both given. Now, what does that tell me? Why is it important to know that these two are perpendicular and that these two are perpendicular? Well, we just talked about it. It tells me that I have at least two right angles, and those right angles will end up being congruent. Now, I have to kind of spell that out in my proof a little bit, but what I can say is that angle RHA, we'll say the measure of angle RHA is 90 degrees. And we'll also say that the measure of angle FBA is 90 degrees. And my reason over here can be definition of perpendicular lines. They're going to meet to form those right angles. So we can say that those two angles are going to be 90 degrees for that reason. Then we can say that since these are both equal to 90, those measures must be equal to each other. Measure of angle RHA would equal the measure of angle FBA, which we can also say in the same step that that means that angle RHA is congruent to angle FBA. You can usually combine saying that the angles measures are equal to each other and that they are congruent to each other. You can usually combine that in one step. And that is by substitution. We just took this 90 and replaced it with what 90 is said to be equal to right here in this statement. So RHA equals FBA, and that is substitution. And so that's another pair of angles. Now we're to that point, like I said, where we at least know that triangle RHA would be similar to triangle, so RHA, R is the vertex of angle 1. We said angle 1 is congruent to angle 2. So the other triangle's name for the similarity statement would have to be ABF, since R and A look to be corresponding vertices. So triangle RHA is similar to triangle ABF by angle similarity. Now, we're not quite to the point where we want to be, but at this point you might just start thinking, well, what does it mean if these two triangles are similar? And like at the beginning of this video, we said that, well, if two triangles are similar, it would mean that all their angles are congruent, which we kind of already knew, but it also means that their corresponding sides would be proportional. And it's kind of like the equivalent to what we talked about earlier in the year with CP/CTC, with the corresponding parts of congruent triangles being congruent. The corresponding sides of similar triangles will be proportional. And I might notice up here that these values are side lengths of my two triangles. So let's see if we can take these values, these segment names right here, and set up a ratio between that would involve those. I would know that HR in triangle RHA would be corresponding to, and therefore I could put it in a ratio with segment BA. And that would equal segment HA's length in a ratio with segment BF's length. Now I know that to be true because of the definition of similar triangles. Definition of similar triangles tells me that these corresponding sides will equal these corresponding sides in a ratio because the corresponding sides will be proportional. So it lets me set up this proportion. Now what I notice is that if I actually use that cross multiplication property or the means extremes property, then what I end up with is HR times BF, this times that, or the extremes multiplied times each other, equaling the means multiplied times each other, and the means are these two terms, BA and HA. And that is, of course, what we are trying to prove. So like I said, we just kind of saw where it took us to say that these triangles were similar, and then we maybe realized that that means that these ratios of corresponding sides would be equal, and then if I cross multiply with these ratios, I end up with the statement I'm trying to prove. So the last thing we need to do is put a statement over here, or a reason, I'm sorry, for this statement. And technically it would be the means extremes property. But if you wanted to say cross multiplication, that will probably be okay. It means the same thing pretty much as the means extremes property. It's easily understood, and that's the key to a proof. So there we have it, a proof using the angle-angle similarity postulate and the definition of similar triangles to state that these side lengths multiplied times each other would equal these other two side lengths multiplied times each other. So another usage of that angle-angle similarity. In our next video, in our next lesson, we'll be taking a look at a couple more theorems, in this case, that would allow us to prove that two triangles are similar, this time getting the side lengths involved. But that's all for now. Hopefully this makes the angle-angle similarity theorem easy enough for you guys to understand. We'll see you next time.